Have you ever just hit a wall with a physics problem, especially those tricky ones where the mass is changing, like a rocket burning fuel, or maybe a cart collecting rainwater? These variable mass problems, they're famous for tripping people up, and it usually comes down to a really common misunderstanding of Newton's laws. So today, we're going to tackle a classic example and break it down step by step.
Ah, this book. If you've ever studied physics, you probably recognize this one. Irodov's Problems in General Physics is just legendary. It's known for these incredibly tough problems that really test if you understand the concepts. And we're pulling a classic problem straight from its pages, one that has definitely caused some headaches for generations of students.
So here's the setup. Picture this. You've got a flat car, and we're going to assume it's on a frictionless surface. There's a constant horizontal force, F, that starts pulling it. But at the exact same time, sand starts pouring onto the flat car from a hopper right above it that's not moving. And that sand is being added at a perfectly steady rate.
And here it is, problem number 1.183 in all its glory. We've got the flat car's initial mass, which we'll call m0. We've got that constant force, F, and we're told that sand is being added at a constant rate, which we'll call mu, measured in kilograms per second. The big question is, as this thing gets heavier and heavier, how do its velocity and acceleration change over time?
So here's our game plan. First, we're going to walk right into the most common mistake. I like to call it the F equals ma trap. Then we'll see why that's wrong and why momentum is the real key to cracking this problem. After that, we'll actually derive the correct solution, and finally, we'll take a look at what the answer really tells us about the physics going on.
All right, let's dive into it. Let's talk about that common mistake. Because when you see a problem with force and acceleration, your brain is just hardwired to jump to one very famous equation.
And that's the question, isn't it? It just seems so obvious. We have a force, we have a mass, and we're looking for acceleration. So why can't we just use Newton's second law, F equals ma? Well, let's go down that road for a minute and just see where it takes us.
Okay, first things first, the mass isn't constant, so we need a way to describe it. At any given time t, the total mass is just the cart's starting mass, m0, plus all the sand that's been added. And since sand is coming in at a rate of mu, the mass of the sand is just mu times t. Simple enough, right?
So the next logical step seems to be, okay, let's just take our good old friend F equals ma and plug in our new expression for mass. So the force F is equal to our total mass, m0 plus mu t, all of that times the acceleration, a.
And if we just rearrange that to solve for acceleration, we get this. A equals F divided by m0 plus mu t. And you know what? It looks plausible. It makes sense that as the mass goes up, the acceleration goes down. But this is wrong. It's missing a huge piece of the puzzle.
So to really get why that answer is wrong, we need to dig a little deeper into what Newton's second law is actually saying. And this right here is where the aha moment happens.
Here's the crucial insight. That external force, F, isn't just doing one thing. It actually has two jobs. Job number one is what we thought of, accelerating the mass that's already on the cart. But job number two is accelerating all the new sand. Every second, sand with zero horizontal speed lands on the cart, and that force F has to speed it up to whatever velocity v the cart is currently at. Our simple F equals ma approach completely ignored that second job.
And that brings us to the more powerful, the more fundamental version of Newton's second law. It's not really F equals ma, it's that the net external force is equal to the rate of change of momentum, F equals dp dt. Now, when mass is constant, this just simplifies down to F equals ma. But when the mass is changing, like in our problem, you have to use the full momentum version. Seriously, if you take one thing away from this whole explainer, let it be this. The moment you see a problem with changing mass, it doesn't matter if it's rockets, raindrops, whatever, your first thought shouldn't be F equals ma. It should be momentum. Okay, theory time is over. We have the right tool now, F equals dp dt. So let's get our hands dirty, apply it to our flat car problem, and see what the real solution looks like.
All right, let's build this up carefully. First, momentum, P, is just mass times velocity. So for us, it's our whole mass term times v. Now, we apply the principle. The force F equals the derivative of that whole thing with respect to time. And here's the key. Since both mass and velocity are changing, we have to use the product rule from calculus. That gives us two terms, dm over dt times v, plus m times dv over dt. And hey, we know what these are.
dm over dt is just mu, the rate sand is added. And dv over dt is just acceleration, a. So we plug those in and we get our full equation. F equals mu v plus the quantity m naught plus mu t times a.
And now it's just a little bit of algebra. We just need to isolate a, the acceleration. And when we do, we get this, the correct expression. Now look closely. It's almost our old wrong answer, but it's got that extra minus mu v term on top.
And now for the moment of truth. Let's flip to the back of the Irodov textbook and, yep, there it is. The final form in the book might look a little different after they integrate to find velocity, but our equation for acceleration is spot on. Our method works. That is a great feeling.
So, great. We have the right answer. We matched the textbook. But what does it actually mean? To really get the physics, let's compare our first intuitive guess with the correct result we just found. Let's just put them right next to each other. The only difference is that mu rv term being subtracted in the numerator. What this means is that the true acceleration is always less than what our simple intuitive guess told us it would be. So what is that term actually doing? And this is where it all clicks. That mu v term is basically the force required to bring the newly fallen sand up to speed. From the cart's point of view, it feels like a drag force, constantly pulling it back. Part of that external force F is being spent every single second just to deal with the new sand, which means there's less force left over to accelerate the whole system. You know, a great habit in physics is to do a little sanity check. Let's look at the very beginning, at time t equals 0. Well, at that instant, the cart hasn't moved yet, so its velocity, v, is 0. If you plug v equals 0 into our correct equation, that whole mu v term just disappears, and we're left with a equals f over m, naught, which is just plain old f equals ma for the cart at the start. It's exactly what we'd expect. Our equation passes the test.
So let's wrap this all up. What are the big takeaways? Number 1, for any variable mass problem, F equals dp/dt is your master key. Number 2, remember that F equals ma is just a special case that only works when mass is constant. You've always got to think about the momentum of the stuff being added or thrown off. And for a little bit of fun, this exact principle, accounting for the momentum of mass being ejected. That is the literal foundation of rocket science.
And that leads me to a final little question to leave you with. The famous rocket equation can be written like this, where u is the speed of the exhaust. Now, it looks a little different from our flat car equation, but the physics underneath is exactly the same. Can you see the connection? Can you see how the force you get from throwing fuel out the back relates to the drag force you get from adding sand on top? It's a really cool way to see how one single core idea can explain totally different things.